Hi, Rama.
Good
So,
morning.
good morning. Yeah. Um, okay. Did you look at the video recordings? And maybe you have some questions or something, some topics what you should specifically cover? I have a question about the homework. Can we maybe see the first picture before we? I checked the video recording and something like fourth video recording from the first of those, or well, that was quite specific explanation how to do it, but we can do it here once again. That's not problem. So just a moment. Who is what did I launch open? Okay, so homework about coding. Toma, have you been able to have some success with the homework? How is your situation with that?
Yes, so during my master's, I did some project that involved running hydrodynamic simulations. So I went back and looked at some of the simulations that I run, and was really analyzing some of that data.
If you have some hydrodynamic simulations actually already available, then you can use those data as well. Okay, just let me speak about more details about that so-called side flow. As you have learned thus far, a big part of turbulence and mixing actually related to the statistics of material elements, like how they are stretched, how they are folded, but most importantly, still stretched. And because of that, it really doesn't matter that much if you have a real turbulence hydrodynamic calculations field coming out, or you take some so-called synthetic field. So let me just to have some trace here. Now it came back, and yeah, now maybe we can start now again. So mixing depends almost exclusively on stretching of material elements. These are lines, surfaces, volumes. Volumes in for incompressible fluid are not remain constant, but in the case of compressible flow, they start also changing in time. And because of that, we can use synthetic flows model well. Now, what are synthetic flows? Synthetic so we have so-called direct numerical simulations, which give you real flows. DNS, direct numerical simulation, DNS. These are like almost like real flows. But DNS, they are computer time consume quite a lot, because if you want to do hydrodynamic simulations, you need to do it in 3 dimensions. And then if you have, if you want to have good resolution, then you can, just there is no way to say, because you'll learn later that in turbulence, smaller scales are created, and you really need to have a lot of pixels. Cost a lot CPU time. And because you really don't need to have real flows for understanding how mixing happens, so it's quite often used, quite often that you use synthetic flows instead. And well, synthetic. First of all, if you have access, of course, you can take some flow data. You don't need to run DNS. But you can take simulation results of DNS, and these are pretty much real. But then again, sometimes even it might have additional benefit of having synthetic flows, because with synthetic flows, you really know exactly what you are putting in. So DNS gives you turbulent flow, but turbulent flow has more complicated statistics than real flows, than synthetic flows. So synthetic flows, you know exactly what the free properties are. Exactly what the properties are. So in terms of understanding the process, it's actually a benefit, because then next step you learn what are the real flows, and then you can combine those two knowledges. And now synthetic flows. Of course, yeah, well, because what really matters is stretching. So you can take as simple as possible field which does stretch. So since what matters in stretching we take simplest flow, but stretch, not stretch. And so what is the simplest flow? That's basically all. Sine flow is one of the simplest possibilities. And so sine flow is such that it first stretches in x direction, then in y direction, and if you want also in z direction. So now again the question 2D versus 3D. 2D, 3D. Real life is 3D. And in some cases, the difference between 2D and 3D is quite important. Sometimes differences between 2D and 3D are important. For instance, turbulence itself. 2D, we have, you'll learn later, that 2D has so-called inverse cascade. 3D has direct cascade. What does it mean? It means that energy goes to larger scales. And so energy goes to larger scales. More moves goes is transferred. It's transferred to larger scales. And 3D means that energy is transferred to smaller scales. Meaning that if you have two-dimensional turbulence like atmospheric one, so these are cyclones, anticyclones. But in smaller scale, you have just energy goes to smallest perturbations. Okay, so this is one difference between 2D and 3D. Then again, in chaos theory, between 2D has no chaos because two integral lines cannot intersect in topological constraint. 2D, no chaos. Chaos if the dimensionality of the phase space is 2. 3D does have chaos. Does have chaos because in 3D two integral lines can bypass each other to space. So like go one around the other. Integral lines integral trajectories can bypass each other in 3D, but not in 2D. So actually, you cannot just play by hand and say it, okay, 2D and 3D are the same. No, because there are cases when there is really important difference between those. But in the case of mixing, it appears there is not much difference. You will learn also later that if we speak about, for instance, about magnetic dynamo, then there is again difference between 2D and 3D. But okay, now I have repeated that already many times. But in the case of mixing of massive scalars, no big difference for mixing of massive scalars. No need, meaning qualitative. Difference between 2D and 3D. There is a small difference, but that's not really that important, which you'll learn later, a little later. But now let us finally go to sine flow. Sine flow. So we have flow where V, X component, is equal to, let us say, sinus, because it's sine, let us be sinus of, I can put here K, but because I can make it dimensionless. Well, now making things dimensionless and from dimensional things is another thing which needs to be discussed. Maybe you know, maybe you don't know. Now raise your hand if you know what is making equation dimensionless. What does it mean? I can see one hand. Toma, what about you? You know. Yeah, so what makes normally difference between physics and mathematics? Mathematicians take already from the very beginning dimensionless equations because they don't care about units and things. Physicists normally start with dimensional things, but here I wrote velocity sinus. I already have velocity now in my case dimensionless. So let us let us make it for correctness first. V naught. V naught is certain constant. V naught and sinus of a k y times y. And now this is valid until certain time period. Now that is a kind of free parameter, but let us say from 0 is less than t is smaller than tau. So during first certain short time period on the order of unity, because if you take it very small, you need to you can also take that tau very small. But what does it mean small? Actually. Let us say tau is on the order of now one hydrodynamic time. So if V naught is speed and K is wave vectors, and characteristic time is scale divided by speed, but scale is 1 divided by K y, right? And speed is V naught. So scale divided by speed, meaning things like that. So we take characteristic time such that during one period here, where the velocity remains constant, velocity will manage to stretch that material lines manage to stretch by a certain factor, which is neither too big or neither too small. So 1 point something maybe. Not 10, not 1.01, but something like 1.1, 1.2, 1.5, maybe something like that. So there is considerable stretching already. This also now that's actually a somewhat important parameter because if we think about what is happening in real life, we want also we make a simple model. We want to keep touch also with real life. So if you have a very permanent stationary vortex, that will long for a long time and stretch also material lines for a long time. In that case, during one decorrelation time, the line can be stretched by quite a lot. But normally in hydrodynamic turbulence, that is not going to happen. So you won't see very long-living vortices in the exact same place. Even if you take atmospheric processes, then cyclones come and go, right? So they are not standing in the place for a long time. Now, there are some flows which are quite stationary in time. Can you tell me, do you know some flows which are very persistent, long-living?
The jet stream.
Repeat once again.
The jet stream.
The trajectory?
No, the jet stream that goes around.
Jet streams, exactly. Jet streams are, yes. So in the upper atmosphere, they are quite long-living because of global atmospheric processes like heating near the equator and cooling at higher latitudes. And this creates like quite permanent flows. The other thing is that the Gulf Stream and things like that, water flows are also quite stationary. And if you take Jupiter, then there is a famous red spot, right? That's also very stationary. Then again, if you go to plasma physics, then there you might have ones which are also very stationary. Now, I am not going to write everything down because if I am going to write, then we will move very slowly, right? Screen has lag, and I cannot write too fast. And sometimes I can go to a laptop and type in, but yeah, but okay. So it's like supplementary material, just not written down. And so there are fields which link long, and that is a parameter which is called Kuban number. Kuban number, KQ, Kuban number. This is basically the ratio of the two time scales. It is that tau divided by ky and v naught, meaning how relates hydrodynamic time to the decorrelation time. And as long as Kuban number is not very big, then mixing, there is no big effect on mixing. But if Kuban number gets big, then things become different. So very big Kuban numbers, meaning that if you stretch during the case of sine flow, if you take very big tau, let's say material line stretched a lot, then we are going a little bit off what we want to have, unless these are really processes when you do have large Coupon numbers in real life. So if Coupon number is like much larger than 1, then mixing becomes different. Different. And if Coupon is much smaller than 1, or on the order of 1, well, normal mixing. We are not right now discussing that large Coupon numbers actually we did consider infinite Coupon numbers. You remember we started with stationary velocity fields, right? When there was an array of vortices what was standing, and then I discussed also a little bit about percolation problem and how it is related to mixing and diffusion in stationary fields. So that is infinite Coupon number case. I studied Coupon to infinity bit earlier. Yeah, so we take the correlation time. Vx is v naught sinus k y y. Vy is 0. We keep Vy 0. And so this is our one of 4. This is called this Vx is v naught sin ky. This is also called shear flow. Shear flow. Shear flow is a flow exactly basically defined by this. You have in x direction velocity which depends on y. And shear flow happens normally and naturally in the case of pipe flows. For instance, if you have a flow in a pipe and a channel, then at the walls the velocity is 0. In the middle it moves, so velocity along the pipe depends on the coordinate across the pipe. But normally it is not sine flow, but as mentioned, we don't care about details. We want to have a stretching, and sine flow does provide stretching. But on the other hand, we also want to have isotropy. We want to have isotropy, so one sine flow won't do, because a sine flow stretches only along y. So in order to have isotropy, we need to switch randomly between different sine flows. So we take now first. So first we have Vx equals v naught sinus k y. Why? Now, as long as t the 0 is smaller than t smaller than tau. Now, let us now consider how we make it dimensionless. So, in order to make it dimensionless, first we need to have coordinate dimensionless. So we take instead of y, we go to let us say eta, which is k y y. We rescale y. Now eta is a coordinate instead of y, but it is dimensionless. Y was in meters, but eta is unitless. So this is dimensionless, the dimensionless coordinate. And then what about the velocity? Our time needs to be also dimensionless. Our time is dimensionless, but if a coordinate and time are both dimensionless, then velocity is also must be also dimensionless. Now, in that case, Vx divided by V naught. Vx divided by V naught is our new velocity Vx divided by V naught. Let us devote it by nu. This is the dimensionless velocity. So we have now eta equals sinus eta dot. Sorry, not I need to still introduce psi because it's x coordinate. X is psi. Psi equals k. We use the same rescaling factor ky times x. This is dimensionless x coordinate. And then we have Vx gives us how material point with coordinate psi moves. We can for tracer we can write psi dot equals sinus eta. And now it's fully dimensionless, isn't it? No dimensions involved. That's what we call making equation dimensionless. And now, depending on the complexity of the problem, you might be able to make your equation fully dimensionless, but you might end up having some combination of constants what you had initially, which goes into a dimensionless number. And then this is a parameter of your problem. So you might have end up having some dimensionless parameter in there as well. In our case, there is one dimensionless parameter. This is a Kubo number, remember, right? We have one dimensionless parameter. And yeah, so what happens now? If we take a velocity field, how it looks like. Okay, this is our box. If we take if line was initially straight material line, then x coordinate is here and y coordinate is over there. Then that line becomes later on wavy thing, doesn't it? Yeah. All if you have different straight lines, they all evolve into the same kind of wavy thing. And then what we do next is we try to make it isotropic. And this way is just to rotate the whole field. So we rotate the whole field by a random. So this was the first step. Apply one sine flow stretching. Second, rotate by the whole thing. And three, apply, go to the beginning and start repeating. But ideally, you add here some randomness as well. So right now there is no randomness, right? You stretch one way, rotate, stretch one way, rotate, stretch again, apply sine flow, rotate, apply sine flow, rotate. Now, ideally, that rotation angle would be arbitrary, random. But if we have our numerical simulation, it's very easy is to rotate by 90 degrees. If you rotate by 90 degrees, you obtain still some nice mixing, which is not exactly isotropic, but almost like isotropic, because definitely the direction x and y are more or less equal, but the direction in between are different, because you never stretch in along diagonal, right? So it is like somewhat isotropic, but not fully isotropic. You obtain still most of the chaotic mixing things come out okay. So qualitatively, you still have a more or less correct things in mixing what you would like to have, but picture itself might not look fully convincing that there is no randomness. There are like kind of regular patterns that are emerging. Now, how you can fix it? Then you can have certain random phase and random directions. Now you cannot rotate because if you have periodic boundary conditions, you cannot rotate by 45 degrees because then periodic boundary conditions no longer work. So you would be able to rotate only by 90 degrees, but you could add some introduce some random direction to the stretching deformation. But then again, the stretching deformation still needs to be yeah. Okay, let us go to the next page. At least, at the very least, what you can you will be able to do is you will be able to write that v nu x equals now sinus k y plus certain initial phase phi. That will introduce certain randomness here. And then you can, yeah, so this is the random number. This is, let us not go into more details, that's enough for you. So we are not going to try to make it more isotropic. We just add here one random number here, random phase. And you will be able to obtain many very relevant features if you do simulation, very relevant features of turbulent mixing with such kind of sign flow. Now, that was like a long story why my motivation speech why sign flow is good for modeling turbulent mixing. And that also gives, I hope, more motivation to you in making that simulation, because this is really what happens in your, if you mix whatever you have, maybe you have, like you're painting something and you need to mix different dyes together, and then you want to them to mix long enough so that it is homogeneous new color, not the separate spots of the two old colors. Then how you would stir this thing, for instance, or if you have a chaotic flow, again, so let me remind you what is chaotic flow. We consider two different things: fully turbulent flow and chaotic flow. Chaotic flow is a smooth one when you have smooth field lines, and the fully turbulent flow is which has fractal streamlines. So if you have right now we are speaking about chaotic flow because of that we have only one sinus here, not more. And now how to do it step by step now before then. In computer, it would look something like that. You take your dye concentration. You initially put some, let us call it temperature. We temperature as a function of x and y. Let us say that initially T xy equals, and let us make it sinusoidal, the sinus of x. Now, periodic boundary condition, it means that our domain for x and y goes from 0 to 2 pi. X, y belong to the segment from 0 to 2 pi excluding. Normally, it is not 2 pi. Normally, you take it from. Normally, you take. In code. X, y The most convenient way is to putting it into domain from the powers of 2, from 0 to, let us say, no, how many pixels? What is a good number of pixels? Tell me, order of magnitude. Toma, which size have you had simulations? How many pixels in one side?
Well, the one I was looking at was a 64 cube.
64 cube.
Yeah.
One side is 64.
Yes, I believe. Yeah, I think so.
Okay, but 64 is very small number, isn't it?
No,
Now,
I mean it's 64 long. 64
yeah,
long.
because that's exactly what I'm saying. If you do like a DNS or something like that, then 64 cube might be the right thing to do. But now we are not going to do those complicated calculations. And we can easily take 2048, for instance, or even more. So that's a benefit. We can have nice high resolution pictures now. And then, okay, there is a small, like if you speak in terms of speed of code, 2048 might have the powers of 2 normally are very good. In some situations, they might become bad, slow, meaning, but this is already quite a bit of thing about CPU architecture. So if, let us not discuss it right now, maybe later if you want. So normally 2000 power of 2 is very nice thing to do. Why? I'll also explain exactly in the context of periodic boundary conditions. So in that case, we have t x y is not sinus x, but is sinus, and now goes 2 pi x divided by 2048. It is still full period in that length, right? If x goes to 2048, we have 2 pi, and we have full period fitting into our range. And now, not to write it every times down, let us denote, let this be my function of x. Because writing that 2 pi and thinks it's long, let us just define this as my fx. Now, I'll be using that later on as well. Oh no, not so fast. I'll be using later a little different thing. Later I'll add here a phase phi. So let me use that fx redefine later. Now, next step is applying the distortion, the stretching. And then we say that t, and this is, yeah, t equal to 0. And now t x y at t equals 1. After 1, the correlation time. Now I can use here the correlation time as a unit step for this integration. And this equals, we neglect the molecular diffusivity and assume that the temperature is just transferred with the flow. So now it is transferred with the flow, and let us say it is transferred in the direction of y. So we say that this is the old function, but it is an old function, but not in the same xy position, but shifted. By shifted by a certain taken from this certain distance. So let me maybe make here a small figure to explain how it is shifted. So we have initial polygon power simulations, and then we have isodensity lines. They vary with depend on X but not on Y. So red is hot region here, and then we have a cold region is here and here. Let us say. We take now pixel values from here, move to somewhere here, let us say. Okay, and pixel from here move to here. You remember it's sinusoidal function. So now we take the old tx values from along x axis from different points depending on y. So it is x minus that new x as a function of y, but y remains the same because our displacement was only along the x direction. So I take okay, this thing here goes into this thing here. Okay. Now, the second thing we need to put here also amplitude, because I wanted to make everything dimensionless, but right now I am running a little into trouble regarding my Kuba number. You remember Kuba number was dimensionless number what we have here, but dimensionless parameter. And because I took correlation time equal to unity, so I lost the opportunity to introduce Kuba number into time over there. But I can introduce it here. So let us say here actually is Kuba number as a factor here, kind of Kuba number. So how, it means how much we stretch it in the one step. If k is small, we in each time step we displace it a little. If k is big, then we displace a lot. Exactly as respectively for small and large Kuba numbers. Okay, and then you could do actually now next step. You could, if you don't want to rotate the whole thing, you can actually add here displacement in y in the same way. Now you can, as a next step, you can right now add the okay. Now next, and this becomes t equals this t equals 1. Now next, let us take t x y. At the moment of t equals 2, and sorry, here was t equals 0 was here. Okay, and this here now equals t. Now the whole thing, but distortion is along y-axis. So we keep x the same, but we take now y and minus, and now it's new y as a function of x. And this equals to, at the moment, t equals to 1 from the previous time step we take. And now if you ask what is this, and then this here is the same thing over there, but change k times sinus k. Okay, we keep the same way vector ky times x plus 5. But ky is actually what is ky? Now it's coming from here. Ky is 2 pi divided by 2048. 2 pi divided by 2048. Okay, that's our ky. All right, so that's and each time we take that phi, we take as a new random number. So it's not the same, but each time we coin from phi, that makes from 0 to 2 pi, right? From 0 to 2 pi. I got a random number from 0 to 2 pi. That's almost the entire algorithm, except we are missing right now periodic boundary conditions. Now, and now comes into handy the fact that we have 2048 as the period. Toma, you have, I understand that you have done with periodic boundary conditions. How you have been handling periodic boundary condition?
I don't think we've actually, or my most recent simulations, I don't think there were periodic boundary conditions.
Okay, all right. So actually, that power of 2 makes very easy to handle. Basically, what you want to do is, if you look here, what we have. If we look what we have here, this thing here. Okay, we need to take x value from somewhere else. And as long as some value somewhere else is in the same range what we have, then there is no problem. But if that value here goes beyond that range, then we cannot just take from some computer something what is not there. So in the computer, there are data from coordinates from x equals 0 to 2047. Yeah, sorry. Yeah, 48 is included. Yeah, that's fine. 2048 is included. Now, it depends also how in different programming languages these arrays are array indices go in a different way. In C++, normally your array starts from index 0, and meaning that the last index is 2047. In some language, what is in Python, starts it from 0, 1? Which one? In Python, you start from 0 or from 1?
You start from 0.
Also from 0, right? I think in some programming language you start from 1, but of course 0 is much more convenient. Starting from 0 is much more convenient, and yeah, so if you end up having in there a number which is outside of the range, you apply boundary condition, periodic boundary condition, meaning that you add and subtract 2048, so long as that you will fit into the range, right? You understand the concept? So let me maybe I write it in a new page, but I would like to take a copy here if I may. See if I can copy this. I copy a lot of more things as well, but I guess delete. Copy. Maybe just Ctrl C from the computer. It's easier to do on my laptop. So you hear an expression like that, and then Now, how do we write it algorithmically? So let me write first by words. If this is outside of 2048, then we add or subtract 2048, so long that the result will be here in this range. Okay. The idea what we want to do is clear, right? Now, how to do it in the best, in the easiest way. Now, let me see how good you are at coding. Tell me how you would do that. So, what is the? We want to have certain x prime or new x or something like that. We want to have memory address where we need to take our data. We want to take it from x minus b x as a function of y. The result is maybe outside of the range. So how shall I fix? What is easiest way of fixing it? Who can tell me? Now is a small numerical method section in our lecture. So because we have most of the things are recording this video YouTube, so I think we can afford a little excursion to coding. So student guys have had quite many of coding lectures. Otto, what any idea? Any suggestion? Toma, maybe you have something.
We just subtract 2048.
You subtract, but then you need to test this if the result is in or out. You can do that. You can have like jumping condition. That's true. But first you need to test subtract or add, and then again, yeah, here is clear that you don't need to subtract or add many times because our displacement Vxy is presumably less than 2048. So you cannot go very far from the range that you won't need to add or subtract twice. But in general case, there are situations when it might go very far from that range. And then you need to check whether you if subtracting once works, if you need to subtract twice, and so on, and that makes code quite complicated. And also the jump condition itself in a code is not very good. Now, guys, do you want me to tell you a little bit, a few hints on how to make a code faster? Raise your hand if you want. Okay. Now, then we need to start a little bit about our computer architectures, what we have nowadays. They have thing which is called pipeline. And a pipeline is, I am not going to write down here because that is, would take, just try to understand what I'm telling and not writing down. Yeah. So pipeline means like that. So each operation, what you make as a code, is divided by computer into microcodes. So that is a thing which you write in your programming language. It might be Python, it might be C, C++, whatever. Now, things are a little different. First thing is that if you want to have fast code, then you can use Python, but you need to use, it is better to use extensions like NumPy or CPy, because normally, and your typical Python code is interpreting the code on the fly, meaning that from your written code, a machine code is produced on the fly, and it is very far from optimal one. And because of that, normally your C or C++ code runs much faster. Now, what might run even faster are those archaic programming languages like Fortran. Any one of you did you have dealing with Fortran?
The simulations that I ran actually used Fortran 95. I'm not fluent in it, but there was it was a pre-written code called pencil code, and I just used Python to interact with it. There was like an interface to.
Yeah, the situation is as follows. So nowadays, Fortran is quite, for most of the users, is forgotten language. But in scientific calculations, it is still being used. The reason being that there exist a lot of ready libraries. On the one hand, ready libraries, you don't need to write your code yourself, but just find a proper library for a function or procedures. And the other thing is that actually Fortran is the structure of language itself is fairly close to what is machine code, assembly code of the CPU. So CPU has certain instructions for the CPU itself, like take something from take data from this memory slot, put into register, then take data from other memory slot and add to what is in the register, store end result into something. So you write in your C or C++ code or Fortran code, this as one single line, but it is decomposed in machine language into those lines. Several instructions. Basic operations being that take from memory address, do something with registers, add, divide, multiply, and store result at some register address. Sometimes you need to calculate that memory address as well. So this makes even some more additional machine code instructions. And now C has also some features which are even a little fuller, take usage of what machine code can do. For instance, a trinary operation of C++, like A is larger than B and question mark and C. Do you know about that instruction? No, nowadays people don't know that. Okay, so this is like you have used Excel, right? In Excel is that if A is larger than B, comma A, comma B. So it can take up normally two, like if else. So first is if yes, and the second argument is if no. So that trinary operation of C is works the same way. It takes logical result, and if it's yes, then takes the answer is the first argument. If no, then the second one. That's also something which is very efficiently can be transferred into machine code. But now I think we are shifting a little bit too much to side from what I wanted to tell you. I wanted to tell you that modern computers have those machine codes, like add, take from memory, store into memory. But the thing is that even those things are like combination of different things what computer does internally. So there are so-called micro-ops, micro-operations. And now for single arithmetic operation can have quite many of micro-operations. If we take multiplications, that has some several micro-operations. If we take divide, that has even more, quite many micro-operations, something like 17 or I don't know, quite a big number of micro-operations for divide. And now what computer does is so-called out-of-order execution. So it starts takes some instructions, looks if it can make the operation now or not. If it cannot make it, it puts into a waiting order, waiting list, and goes on. Let's next operation and see looks if it can make it the calculation or not, and so on and so on. And some operations are being started made, but then there are dependencies. Like our next result needs result from before. Next operation needs result from before, which has not yet retired. The answer is not ready yet, so it is also on waiting list now. And so a pipeline can have this is what is formed this pipeline. Different operations which are on being executed. Some of them are still waiting, but they are already the machine code is decoded into micro operations. And now maybe like 20 or more operations, micro operations can be in the pipeline at different stages of execution. So once they are retired, meaning that the result is ready and everything is finished, then it goes out of the pipeline. It retires from the pipeline. Okay, and now why I started the whole explanation. Now, if you have branching like if condition, if this do that, otherwise do something else. So in terms of machine code, it means instruction pointer jumping to other position. So you take or in the order they are in the computer memory, all these machine codes execute, and now you are at branching point. You don't know where to go, but remember that the computer does it takes into pipeline, and it doesn't know now where to start continuing pipeline, whether branch A or branch B. And now it's what is called speculative execution. Now it's suppose, okay, most probably I'm taking branch A and I start continuing at A. Okay, and then it starts continuing following pipeline along A. And if the branch is really taken A, everything is fine, and computer executes fast. But if branch is taken into B, then everything is wrong, and all the pipeline is flushed, meaning that you lose all those 20 or 30 operations which are on the pipeline. They are like if you make, you can think that if you make produce something and then you discover a mistake, you have produced 20 pieces of what you made, and then you think, okay, I did all wrong and throw away. Something like the same thing happens over there. That you throw all those operations which have been in the pipeline away as no longer usable, and continue from the branching point now towards B. And that can cost quite a lot of CPU time. What does it mean? It means that you should not use a branching which are not predictable. Fourth cycle is quite okay, because now the modern, what is the actually art of CPU architecture is making predictions correct, almost always correct, because each misprediction costs a lot of CPU time. So modern computers can predict quite well if conditions. Even the end of 4 cycles, they can predict quite well that, okay, 10 times I go back and 11th time I fall through. That they can predict. The first time maybe they make mistake, but if you go again, I come back to this point, then they can make it right. But if you have, if your branching condition depends on random number, then it cannot be predicted, right? Each time you go, half of the time you go there, half those branchings will be wrong, and that's what you definitely need to avoid. So maybe I write this conclusion down. First was explanation why, and now the conclusion. Avoid in your code branching that depends on random data. In this case, actually, the graphic probably would not be that random if you make like how Toma suggested, but still there is a danger of quite many time of misprediction. Okay, so that was. Did you get more or less the whole thing? Okay, so. But now, what is then the best way of making the applying the periodic boundary regulation? Any other suggestions after that long story? Okay, so let me write first down one option, which you didn't mention, but probably something which would come up would be like, let us take that this thing here. Instead, we don't take from x minus dx, but not from y, but we take now like that. E now x minus v x as a function of y. That was what originally, but now we make a certain operation with that. And now we take a remainder of division by 2048. Do you think this will work? Reminder when you divide by 2048. You know that percentage, at least in C++ percentage, gives you not division result, but the remainder of division, right? Otto, will it work? Toma, what do you think? Will it work?
Probably better than just subtracting 2048.
Sometimes it does work. First, it is obvious that it works for x, for the argument if it is positive. If it is 2048, sorry, now I am, yeah, it works. If it's 2048, then a remainder is 0. And you take from 0, because 2048 is same as 0 with periodic boundary regulation. If you take 2049, the remainder is 1, you take from position 1, it's clear that it does work, right? And now what about the negative numbers? Guys, do you know at all how the negative numbers are stored in the computer? No. Toma, do you know?
No.
No. Nowadays, no one knows. So it's fun. I was studying some code C++, I don't remember. Probably it was Fortran. We were taught at the beginning how the numbers are stored. Nowadays, no one tells you. Numbers are just numbers. Well, it is useful to know. All numbers are bits. Stored by bits. So normally, if it's an integer, so it depending on how you make your code, but it can be 32 bits or 64 bits. So integer. So it is a sequence of zeros and ones. So let us say 5. What is 5? This is a 0, 0, a binary number, blah, 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 blah. And at the end, you have a 5. How is it in binary? 4, which is 2 to the power of 2, plus 0 times 2 to the power of 1, plus 1. So it will be a 1, 0, 1. Am I right? Ending. So this last one is 1. 0 would be multiplied by 2, and that 1 would be multiplied by 4. That's how it works, yeah? So this is 5. But overall, you have 32 digits. Now, 0. This is, of course, all zeros. But now, let me ask you, if you have minus 1, how would you need to make it minus 1 so that if you add 1, you obtain this? have you ever done addition and subtraction on paper? Like write one number, another number, and subtract or add. Like you have done at least when you were very young, when you did that. This works exactly the same way. So you need to have numbers that if you add one, everything goes to zero. And that's quite easy. -1 is all ones. (32 of them). Because now if you add one, imagine adding here one. One and all zeros, that's what you add. Okay, then you add 1 + 1, this is 1 0, right? 1 is carryover. And then that carryover, you multiply, you add 1 + 1, and then it carries again over to here, and so on, like moves like in domino tower, when you push one and all moves over, right? So you add 1 and it triggers all the carryovers until everything fills with zeros. So -1 is all ones. And meaning that actually this guy here is sign bit. If it is 1, your number is negative. If it is 0, it is positive. The eldest bit is a sign bit. But otherwise, it works exactly the same. And now division means also you can just, in terms of dividing, you can take the number, what you have at hand as a big number with you can interpret this as you like. You can interpret the latest one as a sign bit or as an unsigned number. So actually your computer code, actually maybe you know it, you can define variable, at least in C++, as unsigned number or signed number. They are stored exactly the same way, but if it is a signed number, you lose 1 bit because 1 bit is a signed bit. If you have unsigned number, the last bit becomes the most significant bit. So it unsigned integers are 2 times bigger, can be 2 times bigger than unsigned one. Anyway, the conclusion is that yes, even if it's minus, it still works. You can still use the same percentage. But now actually it becomes also clear how you can do it much easier and faster. Because what is the problem now with that? That's okay. Okay, fast and slow. Why it is slow? Because division is slow. And furthermore, you need you use the result for addressing. So you remember about the pipeline. So if you take the number, you first need to calculate address, and only then you can take the value from that. And this adds additional delay. So you would also like to avoid to have faster code, to have not that many calculations with your indexes, index values, array index values. And this someone who is not that good in coding would probably write that code, which is slow. But you remember it took the power of 2, and that is with a good reason. Because now, reminder with dividing to the power of 2 is actually zeroing all the other bits except for those last what we need. To 2048, how many bits you use over there? It is 2 to the power 11, right? But we won't go quite to the 2048, we stop at 2047. So we need use the same number of bits as we would use for 1024, which is 2 to the power of 10, which is 11 bits still, because 2 to the power 0 needs 1 bit, 2 to the power of 2 needs 2 bits, and so on. So 1 more than it is. So basically, this thing here is simplified to x minus mu as a function of y. No, sorry, E of x X is not also too well written. Let me try writing better. X minus new x as a function of y, and now we take what is called bitwise n, which is 2047. That's it. Now again, can you guys see that this will work? Let me make that more like the other one. Can you see that this will work? You probably are telling me that you don't know what is bitwise n. Raise your hand if you know what is bitwise n. Toma, do you know what is bitwise n?
I don't understand what you're saying.
All right. Which means that you don't know. So that's actually again a thing which is, I think it's something which should be taught during IT courses, coding courses, but you have in C you have a do you have something like that? This A and B, logical operator. So what does it mean? It means that this is 1 if A or B equals 1, 0 otherwise. But then there is A and bitwise n. And that's the same thing, but with bit by bit. So if you have A is, let us say, what do we take? Maybe 30. And what might be B? Can you tell me? Any suggestion? For B? Not too big, but we can still convert into bits. Maybe something like 5. No, let it be 5. Yeah. So okay. So this is 8 plus 4 plus 1. Easy. This is 4 plus 1. Now A is all zeros until 1, 1, 0, 1. B is all zeros 0, 1, 0, 1. And now goes bitwise n. Now we take bitwise n with all the bits separately, A and B. This is 1, this is 0, this is 1, this is 0, because 0 and 1 gives you 0, doesn't it? And all zeros, okay? So this is 5. Now, what I suggest to you is that we make bitwise n with 2047. So we have A and 2047. And then we have A is whatever. Let us take something. 0, then 1, 0, 1, 1, 0, blah, 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 blah. 1. Altogether, we have here our range is 11 bits. We agreed that our index spans through 11 bits because it's from 0 to 2047, which is all ones, so 11 bits. And now 2047 is all zeros, but this is 12 bit, right? I wrote here 12 bit as 1. This is 0, and then go all ones, 11 of them. because I take now bitwise and all those numbers for A remain as they were because making bitwise and doesn't change them at all. But anything which is over here goes away. I use like a mask. 2047 works like a mask, which makes all the rest zero except the lowest 11 bits. So the result what we want. So this belongs now to the range from 0 to 2047 included. Okay, can you see that? That's exactly what we wanted. And it is regardless if we have plus or minus. If we have minus, then you remember we had all ones at the left-hand side, but they go away because I apply mask 0. It's a very easy and nice way of applying periodic boundary conditions, and very fast, because bitwise AND is one of the fastest operations there is. As fast as plus or minus, adding or subtracting. Okay, Toma, is that okay? Did you understand?
I don't think I got the last part. Like I got the A and B, but not the A in 2047.
Okay, so bitwise AND takes into binary writing the two arguments, and each corresponding bit, like smallest, the last bit from two numbers, we take bitwise, we take AND. Second smallest, we take also bitwise AND, and so on with all the bits there are. Meaning that if we have, we make with any number a bitwise AND with 2047, and then we zero all the bits which are out in the slots from 12th bit up to the 32nd bit. Makes them 0. What remain are only the bits which were in the 11 smallest slots, which corresponds to a number from 0 to 2047. Raise your hand if you are, I can try to explain it once again, but raise your hand if you understood how it works. One hand and not more. Maybe I need to explain once again. Okay. And actually that bitwise AND works the same as a bitwise OR or bitwise XOR. They are working exactly the same way. Once you understand one of them, you understand all of them. So any just to not to write too many bits. Let us assume that we have 8 bits in our number. So variable char is 8 bits. Unsigned char or signed char is 8 bits. So it is a binary number which is stored in computer memory as 1 byte. 1 byte is 8 bits. So, for instance, number 7 is we start from the end 1 1 1 1. Because maybe I wrote too many. So this is 1, this is 2, this is 4, this is 8. I write too many. So actually, what I wrote was 15. What I wrote was 15. Let me fix it into 15. So this is 15. And all others are zeros. 8 bits, right? Now, minus 1 is all ones. 1, 1, 1, 1, 1, 1, 1, 1. But it is also the same as now 255. In terms of computer, is 255. Minus 1, if it is signed number, 255 if it is unsigned. Exactly the same thing. Now,
And if we take now bitwise with these two numbers, bitwise and operator, binary operator, which is written like that. Then the result is 1 and 1 is 1. 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 1 and 0 is 0. 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 Okay. So we zeroed all these 4 elder bits because our mask had 4 zeros. They zeroed everything else what was in there. Now let us take now something with minus 3. Minus 3, what it is? It is we add here subtract 2, which means that 2 is here. That 1 goes away if we subtract 2. This is now 1, 1, 1, 1, 1, 0, 1, 1. Yeah, that is minus 3. Because if you add 2 and 2 is 1, 0, 0. Sorry, not that. 1, 0, 1. Well, this is minus. Okay. And now let us make bitwise and with 15. Bitwise and is 0, 15 is 0, 0, 0, 1, 1, 1, 1. Now with those two numbers, bitwise and is 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, 1 and 0 is 0, 1 and 0 is 0, 1 and 0 is 0. Basically, so we have the same number what we had before, but we take our mask zeros all those. So we remove all those, and what remains is this one here. This is what goes over here. So making our mask, taking bitwise and with 15, because 15 is something which has 1s in the lower bits and zeros in the higher bits. It removes everything, bitwise and removes everything which is in higher bits. Now the result is, what now? Now what is the number here? It is 1, 4, 1. 1, 4, 8. 1, 4, 8 is 13, right? This is 13. Now, our boundary condition has now, because we take 15, this is 1 less than 16. So this corresponds to periodic boundary condition with 16. So now 13 and minus 16 is minus 3. So we wanted to have a periodic boundary condition with minus 3. We see that minus 3 and 13 correspond to this period of 16 as we wanted. So we take our minus 3, we take bitwise one with 15, and we have now index value which is exactly what we wanted. Now, does it become now more clear how the bitwise and works? Toma, what about you? Okay. I think this is very useful knowledge because if you didn't learn it during your computer classes, then that's definitely what is used at least in the more advanced coding. And not yeah, well, I would say more advanced coding because if you work with you see what is a benefit. If you have a lot of data, there is also in computer, but not only on the computer, there are numbers which works as flags. You can take 1 byte, which is 8 bits. And if you take it normally, it is just, you use one number in your computer memory. But it has 8 bits, and if you have question yes or no, actually you can answer 8 questions here, yes or no. So you can store a state of a yes and no state of 8 things in a single number. And that's in terms of computing, it is called flags. So each of those bits works as a flag, and you can test if the flag is set or not if you take bitwise AND. If you want to see if let us say a third bit is set in the number, then you take bitwise AND with 4, because 4 is 1, 0, 0. It is a third bit. Okay. But more importantly for you, because you are most likely, although it's not excluded, who knows where you go later on, you may go also some computer engineering. In that case, you might be able to use it that way. But for you, for periodic compound organizations, this is in physics quite often used, and this is very handy, because first, the code is much shorter, and more importantly, it's much faster. Okay, motivational speech for me. Okay. No. Basically we ended explanation of how you can make your periodic compound organization. If you go back in the previous slide, you have the code how you make it. Not the slide before. So here, where did I write? Yeah, I wrote it here. Let me box it. Let me box it. And this is the operation what you take. You take your index and make bitwise AND with 2047, because 2047 is all ones for 11 bits. Take bitwise AND as well with that, and you obtain exactly what you want. Gives you periodic bound organization. All right, and with that, your code will become really simple, doesn't it? Now, if you want to make a very good simulation, there is still one issue to be addressed. Who can tell me what is actually still not that good in our example over here? In our algorithm, what is a little problematic here? Can you tell? All things fine. Raise your hand if you think everything is fine here. Seems to work for you. And don't be shy if you really think so. Raise your hand, because yes, there is something wrong. But I'm going to tell you what is something wrong. But just to get the feeling, do you think it's more or less okay? Yes, it is more or less okay, but what might be still not quite okay? Where is a small problem? Can any one of you pinpoint? With that code line. So let me just to make sure. Let me write once again here. Until let us take now next slide. Yeah. So what we have is we take t at x y a certain moment t equals t x minus p x as a function of y and t at the previous moment of time. That's our code right now. I'm sorry, I forgot here to add set bitwise AND. What has a bitwise AND? Now this goes also into braces, and now goes our bitwise AND with 2047, and then goes t minus 1, and braces close. Okay, that's the statistic code. That is quite good code, but it's a small issue. Now you had some time to think about it. What is a small issue here? Small problem. What might be still that? Periodic bound organization is nice, if perfectly executed. No issue whatsoever with that. But okay, think about the index values. Index values here must be integers, right? X, Y are integers. But Vx is not integer.
because it comes from sinus, doesn't it? So Vx is k, the Cuban number multiplied by sinus. K is presumably, actually the Cuban number is not exactly Cuban number, it's a scaled Cuban number, because Cuban number 1 is something like 1.5 is something like, no, Cuban number 1 is that the two times are more or less equal, the formation is on the order of 1.5, but here actually the formation of on the order of 1 is like if you scale it has 2047 pixels. If you displace it around like 1,000 pixels, maybe that's order corresponds to Cuban number 1. So the multiplier to sinus is like a few hundreds or up to 1,000. You need to figure out what you take. You can tell if you have working code, you can just test with different Cuban numbers. But Cuban number doesn't need to be integer. There is no really benefit of having it either integer or a real number, because sinus is anyways gives you non-integer values. So either way, Vx will give you non-integers. So now the question is how to deal with that non-integer. So if I write it just like that, that bitwise operation needs integers, because bitwise operation can be done only with integers. So basically the code, if it doesn't throw out error, then it just converts x minus Vx into integer. And it will work more or less. But what happens is that, let us say we have pixels. Here is 1 pixel. Here is the next pixel. Okay. And now we want to fill in some new pixel from between those two. So this is t minus 1. T equals t minus 1. Sorry. T equals t minus 1. And here is t equals to t. A little cumbersome way of writing it, but I mean this previous step. And now this new takes value according to this displacement here from somewhere else, and let us say it is supposed to take somewhere from here, in between those two. So what is the best way of doing it now? What do you suggest? Anyone? So if it is more or less integer, then it's quite clear. It just takes the pixel value. But now it is in between 2 pixels. Which value we take? Which value we take? Interpolate, yeah. That's quite good. Good suggestion. Now there are a few things to notice still. Now, remember, I showed you what happens in the case of mixing. In the case of mixing, the lines become longer and longer and longer if we stretch, and distance between them goes shorter and shorter and shorter, because it is overall it's incompressible. So initial wide stripe of warm water becomes a very narrow stripe of warm water. And if we neglect molecular diffusion, we just take pixel from one point and place to the other point. But if it becomes very small, the effective Becquerel number also is no longer small, which means that actually in molecular diffusion, if the stripes become very narrow, molecular diffusion starts mixing them. And you can say that if we match our pixel size properly at the so-called dissipation scale, at the scale where diffusion happens, then actually, as suggested here, the interpolated or average value matches real life very well. But because what mixing means
that say average, the mix takes the average value. Okay, so even though it's kind of seems artificial, just how can we substitute average? And it might be not okay or okay. So it is okay if our mixing scale is the same as the pixel size. If mixing really happens as pixel size, you can just take average and say that, okay, this average actually, I take average because the mixing happens and the two volumes of water, hot and cold, are mixed and take average value. Okay, but you need to match. If you don't match, let us say that mixing actually happens at much smaller scales, then what you have might still be something, but not necessarily the temperature itself. So let us say that you have 1 pixel temperature like 5 degrees, but it doesn't. In that case, it doesn't mean that it's really 5 degrees, but it may be maybe 50 and 10, fluctuates between 50 and 10, averaging in 5. Oh no, not 50 and minus 40, 50 and minus 40, yeah. 50 and minus 40 averaging in 5. In that case, your computer code shows smooth average pattern, not real pattern. But if mixing happens really at pixel size, then that minus 40 and 50 really mix into 5, and your pixel really has the same values as what would be in real life. Okay? So what I'm trying to convince you is that sine flow, although it is very artificial and very simple, it actually can describe real life reasonably well. And now shows the perfect flow now would be T at x, y, t equals maybe we write first certain x1. If we define variable x1 as we convert into integer of yeah. In C, you don't need to write here. You can just follow the number. So it's integer of x minus bx as a function of y, and bitwise n was 2047. And then maybe we define, just for convenience, let us define this whole thing here as a floating number. We don't need to okay, so T is now T x1, and now at the moment point y at t minus 1, and now we take a weight. How close it is to the real pixel here? So the real pixel value is here in the braces, and now this is the real pixel value. Yeah, this is, let us define it as x naught. This is x naught. Okay, and now how far it is x1 and x1 plus 1. So if x1 is exactly x naught, we take just from x1. But if it is okay, so let me write it, and you can see if you like it or not. So it is x1 plus 1 minus x naught. This is the weight here. It's the first weight. And the second weight is going to be to the other pixel value, x 1 plus 1, x1 plus 1. Because taking integer truncates the number, it's like floor function. If this is the real number, it takes the floor of it. Truncates the fractional part. x1 plus 1 is a neighboring pixel, y t minus 1. And now we take another weight, and the other weight is how far is it from x1. the sum of weights is 1. So we know, don't need to normals. No, otherwise, if the sum of weights is not 1, you will need to divide everything with the sum of weights. But here the sum of weights is 1 already. So weight is how far it is from the other pixel. So this is, we take value from x1, the other pixel is x1 plus 1. And we take how far it is from the other pixel, take the weight, and here we take for the other pixel, we take the weight as how far it is from the first pixel. And that gives you the interpolated value as such. As Mike suggested. Okay, does it make sense, Toma?
Yep. Okay.
And now, if you do all that, at the end of the day, you would need to you would have quite a nice picture. You need to visualize it. So you can how to visualize in Python. You probably can do it quite easily. Can you? If you cannot, you can just ask ChatGPT to do it for you. You have matrix. Ask ChatGPT. I have a matrix. I want to visualize. Write it down as a GPG. And I think such simple task ChatGPT does very well. Nowadays, it's quite easy. A few years ago, it was you need to study how the hell I am going to, if I have a matrix, how write it as a GPG. But now, okay. And then you can enjoy your picture. You can actually this is maybe you need to instruct or scale something like you have values from 0 from -1 to 1. Remember, yeah. You can just add, make it from 0 to, because if you take grayscale, it goes from 0 to 256. It's 55 usually. 0 is black and 255 is white. And then you can make it black and white, or if you want, you can make it also color. Doesn't matter. Black and white is fine as well. And then you have nice picture, and you can enjoy it and see if it really looks something what might happen. You have as a reference, you have one picture what I showed you before, what is comes from real experiment. Well, it is not going to be exactly what is in that figure, because in that figure is real life. What is some like blobs are more pronounced here. You have also blobs, but they are more homogeneous because you have more homogeneous mixing here. You have no standing places in the tank. You might have some regions which really don't move much, and so it will be more homogeneous. And now, how many steps you will take? Just have a look. You can start first to see if things go nicely. You might take only just observe after 1 step, after 5 steps, how it evolves. That's also very quite instructive. Just to get the feeling of things, how mixing happens in real life. It's not real life, it's sine flow, but as I try to explain you the whole morning here, that artificial flow is a good match for real life. You know, physics is the art of making models, and here a sine flow is a good model. It is very simple, but it reflects reality. All right, now I think almost half of our time is over. Maybe we can make a small break. How many minutes do you want?
5 minutes.
5 minutes. 5 minutes break. 12:30 local time. Probably Toma has 11:30. Yeah. Okay, 5 minutes. With that, I'm kind what is your feeling? Can you do the code now? Raise your hand if you think you can. Okay. If you cannot, the worst case scenario is that you ask
a code from someone who has it and try to study and understand it. That's works also fine. It's best if you can do it by yourself. If you cannot, just get the code and try to understand. This code actually can kill you error. There is still one very small mistake, but what can actually prevent it running properly.
mis me lõpetame, 14.30 või?
Jaa.
Yeah.
14, alustame 10:30. Teeme ka 3 tundi, võib-olla 4 on äkki liiga palju.
3 tundi.
3 tundi. Ma arvan, et niisugust 4 akadeemilist on veel OK, üle selle võib-olla läheb.
Kas meil on jätkuvalt siis veel alustame tund aega varem?
Nii kaua, kuni me saame enam-vähem järje peale, aga nüüd on veel väike asi tegelikult selline, et mul on järgmine nädal, mul on ka omane ära. Aga viimane kord, kus me eeldatavasti selle semestri ära oleme. Ja terve kord jääb meil ka ära. Nii kaua, kuni me järje peal oleme, jätkame 10:30 pärast, kui on tunne, et me oleme järje peal, siis läheb. Toma, if you are still there, we had a short discussion here. So we have right now 3 hours each time. But the thing is that next week again is the week when I am away. But presumably the last time this semester. So next week again, there is no lecture, but we continue having starting time 10:30 and 3 hours until we feel like we are more or less on the track of the lectures. And then we continue normally. We can also calculate how many it should be if we normally would have 2 hours per lecture, and we're missing 3 of them, right? So you have missed 2, right? Is that right?
Yes.
And now it will be 3rd next week. So we are kind of missing 6 times. So it would be overall 6 lectures which start at 10:30 and after that 11:30. We have now this is our 2nd time. So 1 month still to go. So for 1 month we still have we start at 10:30 and after that we switch back to 11:30. That's the plan. But just each time I just confirm it over. Meie see uurimiste seminar, mis päevaks me leppisime kokku, mitmes see oli?
29.
29. Ma ei unustatud kalendarisse panna. No, guys are still not back, but no, I did. Ma panin tegelikult. So I was telling that there is still one small mistake here in the line what I wrote. And the issue is that, look, X1 is guaranteed in the range from 0 to 2047, but not X1 plus 1. X1 plus 1 might be 2048. And if you ask data from 2048, it doesn't exist. Or you might, I say it does not exist, in which case you get something like a memory access error or something and code crashes, or you take from the wrong place. Now again, it comes down to architecture of the computer, but basically in your normal line, if you take next pixel, actually it is the first pixel of the next line. So either you take it from the wrong place, or if it is the last line, you ask something which is outside of allocated memory, in which case you get memory error. So to fix things, actually this guy here needs to be substituted. This guy here needs to be substituted actually with X1 plus 1, and again the same, and it's 2047. Then we make it here again into something which fits into range. But no problem with here, with the multipliers. These are perfectly fine, but this place here needs to be fixed. All right.
Now, will the materials will be uploaded somewhere? Like from last lectures as well?
Yeah, I uploaded the video, yes. So it is in YouTube now. I did it only today, so if you checked it yesterday, sorry about that, but it is now there. If I don't download it during week, it gets deleted. So I did remember to download.
How about the slides? Like,
Slide, I did not send you slides. Right. Okay, now I send you 2 slides together. Sorry. But then we can go on. And now, yeah, well, because we spent quite a lot now on the code and homework, then now we need to go on with theoretical material, and I presume looked into selection. Maybe you have something what is not clear in the lectures and you want me to help, or probably to go through everything, it's a little too long and we will not be able to go everything. So like I'll try to rely on you having had a look on things. So first think about if you have some questions, and if not, then I am going to discuss I discuss about like that scuba number thing a little more. What is the difference between very small Kuba numbers and bigger ones? And I think we did discuss a little about how gradients evolve and some equations. Maybe I'm not going those equations. I looked also at the recordings, and these equations are nice, and I myself like them very much. But then keeping in mind you and specifically what might be useful knowledge for you, then maybe those equations exactly are not the thing what you first and foremost need. What you need more like a general qualitative overview and understanding. And that's why maybe my suggestion is that we are not going to go through all the equations what are written in the lecture notes. These are available in the earlier video recordings, and they are most of them are also in the lecture notes. I think you can look over there. Let us just have more qualitative things to discuss here. Or if you want to ask, then of course we can go to the equation as well. But Toma, what about you? Do you have something what you want to ask about those lectures? What do you have read and what you might have looked?
About the past lecture or the current one?
Sorry?
About the past lecture or the current one?
But yeah, everything. So what we have had past thus far, and those which you are up to lecture. Let us say lecture number today is what? We have had with you third lecture, right? Is that right? Fourth is right now. Sorry, but we need to catch up. So actually, schedule would be something like 6, because we missed 2. So let us say lectures 4 and 5, maybe. The topics of lectures 3, 4, and 5. If you have anything to ask from the video recordings. Let us not discuss yet 6 because we're catching up. We are at the lecture 4, but we need to catch up to 5. So from the video recordings and lecture notes, lectures 4 and 5 first and foremost. What about we take take out the old recording and see, just fast forward to see what is over there and what needs to be discussed more. Just because I think it's like they are already available there. I think it's a little bit waste of time if we do it again exactly one to one. Let me open YouTube. No. I now share with Torma also the other screen. Okay, yeah, bachelor's law is one thing. What we need to do, maybe it's worth discussing. In manage, yeah, here is equation, and I said that maybe we don't stop on those equations because they are nice and all, and I like them. But and we also actually had a little them. And yeah, this is also we had last time a little about convolution and things. But the next thing up is indeed is the bachelor's law. And here is also what is kind of related to the other next topic. What we have here is so-called large deviation function and large deviation function and the statistical conservation laws. Maybe do you want me to recap a little those things? Large deviation function and statistical conservation laws. They are not that mathematical and probably somewhat useful. And then the next thing is bachelor's law. Let us write here three things to discuss. All right, so second. So first, large deviation function. Now, what we did last time was that we showed that the distribution of material line lengths evolves into log normal distribution modes. Was it something like that? Length of material lines evolves into a log normal distribution. I remember how we considered like after one decorrelation time, line is stretched by a certain factor. Then after the next correlation time again by certain factor. So in logarithmic scale, it obtains always a certain increment. In logarithmic, a logarithm of length grows by a certain increment. And then these are random, they are always
bias towards positive increments, not negative or positive growth in average, but the steps are different. So you have two things going on. First, growth, more or less linear in time, and then a random walk around the main value. And this gives you a random walk probability distribution function is a Gaussian function. So it is a normal distribution, but in log scale, so it is log normal. So we learned. What we learned is that that if we have in this scale, we have logarithm of length of a material life. And here is no, vertical expedient. Vertical expedient. Is here. Yes. What happened before that? That I cannot write one. It was just maybe switched off that screen and then again like something like that. Right. Yeah, Thomas, we are having the same problem we had last time, but let us see if it now works. PDF. Yeah, now it works. PDF. And here is logarithm scale. And then it now evolves something like normal in this case, which is log normal. Now, but this is only approximately because what it would be exactly log normal if the jump lengths would be very small. So log normal distribution is valid for normal distribution is valid for diffusion processes. Brownian particle makes very small steps each time as compared to the system size. But if basically in this curve here, if the step sizes which it makes, let me somehow try to depict here. Each next time your length, suppose length was here, right? At certain moment of time, t. Okay, now after the correlation time is moved somewhere here, t plus tau. Now, if that length is much smaller, jump length. If that jump length is much smaller than the characteristic curvature of here, what they have, then it would be almost ideal Brownian motion. But if that jump length, what happens during correlation time, is comparable to characteristic size, meaning that's the width of the PDF, then in that case it is somewhat close to log normal distribution, but not quite, as a certain departure from it. And so now what comes into play is what is called large deviation function. Because what sometimes matters is large events, very long increments or otherwise very short. So in turbulence, it's quite often what you look for is extreme events, because extreme events can be important.
Normally it goes like that, but sometimes very seldom, but you cannot neglect if something big happens. So it's also that sometimes you want to know about those extreme events. And the thing is that actually the main important departure from log normal happens at the end of this distribution. And so let me take new slide. Let us see. Let us plot here now log plot. Ln PDF. And here logarithm of scale, ln n. And now we start with, at the first moment of time, at t equal to 0, our curve is something like that. We have very narrow distribution. We fix our line length and start look how it starts evolving. And it evolves into at later moment of time, it becomes wider. But now, if we take a logarithm Gaussian function, PDF is speed e to the power of minus x square, right? If we take logarithm, minus x square remains, it's parabola. So logarithm in log scale, this becomes a parabola, something like that. And later on, it moves towards longer lengths. Remember, it grows, the line length grows and becomes wider. Okay, as time goes on. T grows and T grows. Okay, now, but we know that it becomes moves to right and becomes wider. That's what we are not so much interested in now. We want to know the shape. So if the shape is Gaussian, or there is a departure from Gaussian, from parabola. So now I somehow need to have a sort of so-called data collapse. In physics in general, and if you have made simulations or some numeric some experiments, what is quite important on the is to be able to find how system behaves, like systematic features of the thing you have at hand. And what is nice is to be able to find so-called data collapse. Here we have three curves, and they are all different. Data collapse means that we somehow rescale those graphs so that they all look similar, the same. So what needs to be done here is to move everything to the same place around axis and make it like narrower or wider, right? Rescale horizontal axis, shift and rescale horizontal axis. And now we know that this distance here, where it goes, is proportional to the time. This is certain lambda times t. Lambda we call Lyapunov exponent. Lambda Lyapunov exponent. No. Exponent. And then it becomes wider, and which becomes certain square root of sigma times t. Sigma is the dispersion of this thing. Actually, that now to have Lyapunov exponent, you would need to divide the distance, this distance here. Okay, actually, see. What the hell is happening? It still works. No, it still works. Yeah, something like our screen again black and said just a moment, and now it's nice still works. Okay, actually you need to extend this to the middle point of this graph. Actually, the middle point is the distance of lambda times t. The Lyapunov exponent. Now, if we take any other point, we can call this a finite time Lyapunov exponent. So this is lambda t is Lyapunov exponent, but if we take another point here on the curve, so
our specific curve might end up being here and not there. And then we say that this you can call or also lambda finite time times t. So lambda finite time is logarithm of x divided by t, just like that. And lambda is I don't like that screen. Just again, just simply stop responding. Lambda times t. It's the same old thing. Let me switch it again. Wow.
I'm not sure if it's a problem of my that open board software or is it problem of the system.
Yeah, sorry about that. All right, finally, what we left at. Now let me try to delete what was not actually needed here. And yeah.
finite time that will not explode. And I was just going to write that lambda is average of lambda finite time. That's how it is defined in Lyapunov exponent. And now I said that if the Kuban number is not very big, then we have more or less a Gaussian distribution, meaning that those curves here are parabola. And now, but if it is not that small, and in real life it is not very small, but it's something on the unity, then there is a departure from the Gaussian function, and we want to study what is its shape exactly. And then we want to have data collapse. How do we achieve it? We are working with Lyapunov finite time Lyapunov exponents. We take logarithm of L and divide it by t, and then we have this kind of shape but now because we divided the t, we bring them all back to the same position along horizontal axis. Those rightwards always, but if we divide it by t, then we fix it in space, isn't it? And then if we need to also to fix the width now. If we fix the width, then what we need to do? We need to take a little. So we need to take the difference between finite available exponent and the average value. Finite time minus lambda, which is a Lyapunov exponent. And then this is departure how much the given point differs from the center point of the curve. So basically, this is this distance here over that. What is lambda finite time minus lambda. And then I want to fix the width, which is square root of sigma t. Then we fix by width. And then this divided by t. All right, something like that. And then we take the square root of t. Square root of t. And then the square root is not very nice, so it's better to take it to square. So it becomes now lambda finite time minus lambda and well. And divided by sigma t, plus t, sigma t. And then we fix its shape. So if we now make a graph, then how it would look like more or less. It would be something like that. We have now some kind of universal curve. Here is here is the thing. So here is the horizontal axis is lambda finite time minus lambda divided by square root of t. Yeah, and vertical axis is probability. And then for Gaussian, it would be parabola, but now the shape is not parabola. And so here, the departure from the parabola, actually, the question is how this end here behaves, how this part here behaves. Okay. Okay. So the question is how the finite time Lyapunov exponent behave. Is it how far is it from the Gaussian distribution? That's all about a thing called the large deviation function. So what I got here is basically the large deviation function, which is the large deviation function. Okay. So now let us try to rewrite it mathematically a little. What I'm looking for. So we have our PDF. is going to be something like that. P equals e to the power of certain function, it's called the entropy function of lambda, but lambda is logarithm of L divided by T. Logarithm of L divided by T. And now to fix it and multiply certain factor. And now what the factor is, you can think about the case of very small Cooper numbers, then this PDF will be Gaussian. So we know that if Cooper number is very small, then P, now again the same thing happens.
The reset that this start, I'm not going to repeat all things, but I just start the software. Maybe I still need to download the newest version. If k if k is much smaller than 1, then p, it was log normal, right? It was something like without factor, let's just like proportional to. Is proportional to e to the power of, and now what total function is minus logarithm of L minus Lyapunov exponent squared divided by a certain form sigma t, which is the dispersion. So this is the solution of a diffusion equation, and the function is out from diffusion equation. Sigma is what is the spread of those steps in logarithmic scale of the material lines, and lambda is the average growth rate of them. Now, if we compare this and that, so if we plug in here function logarithm of L divided by t, we know that this goes to square, so that would be divided by t squared, but we have here t. So now apparently we need to multiply this by certain t. So actually this is the typo. Let me just delete it. We just need to put here some scaling factor t. And then this guy here is what I drew before, the graph. Then that so-called entropy function S of lambda finite time. This is entropy function. Entropy function. Also a large deviation function.
large deviation function. Because why a large deviation function? Because you mostly want to use it if you want to know about extreme events. So if you plot here S, normally it would be a Gaussian function, but now it has certain departure. Left hand side is a little faster fall off, and the right hand side is slower. So it has more large deviations because this is lambda finite time. This is expressing how material lines are lengthened, and extreme event means that they are very more stretched than normally. So large deviation, you will be able to see how it deviates from the Gaussian distribution, and sometimes this becomes important. So these are concepts which now and then surface out, so I more or less know already what is going on in those cases. All right, and now I am skipping here. There are different things related to that. Like points where they intersect and slopes here are some important parameters here in this graph, but let us skip those details right now, and instead let us go to the statistical conservation laws. And for the time being, let us use that simpler form, which is valid for small Cooper numbers. And let us take the slide. Let us consider average of length of material line. But certain power of the material line. Suppose I want to see how the certain power of the material line grows. And then this will be integral L to the power alpha, and then goes to PDF. So real distribution function. So this is e to the power of, and now it was minus L, logarithm of L minus lambda divided by sigma times t. That is squared and divided 4 sigma times t, and then I need to integrate over lambda. DL. We weight the length, which is probability we have. And now this integral is something what can be taken and calculated. And I think this was also one of the homeworks during previous years. So we can leave it also first as an exercise, taking that integral. But what appears is that for certain exponent alpha, actually, average value is constant, does not depend on time. So overall, you are expecting to be grow as above a certain. It depending, but a certain exponential function, because this is exponent. You need to find the close exponent basically of n to the power 5. And now let us show that there is, if we take alpha equal to minus d dimension of the space, then this average value is concerned. So it appears that 2d L to the power of minus 2 is constant. Does it seem like logical? Do you think it's obvious? Not really. Actually, the proof we won't need nothing like that. And you also remember that this works only for exact only for small Kuba numbers. A number much smaller than 1. But this actually is always exact. Exact meaning is that actually if you use this, then you might even get the wrong conclusion. You need to use exact large deviation function here instead in order to see that it is constant. So there might be a difference that using this Kuba number, if you want to calculate how certain power of lengths of material line grows, for I minus 2 is constant, you need to have exact probability distribution function and not the approximate substitute here. Now, how to see that this is constant? It's actually quite simple. We consider first, we start with circle and a point here. So what is it? So we take initially consider material line, our material line which connects one point on the circle and the central point, a material line. But then we consider all possible points on the circle. We average over all the possible positions. We average over all the possible positions. And that's what's going to happen. And now we need to know into what evolves this circle in a long time. So you learned that the overall lines become longer. So this becomes an ellipse. So this evolves into ellipse, something very long. Okay, but the surface area is conserved because it's incompressible fluid. So we have center here, and now our line evolves into something like that. And now we take 6 to the power of -2 and average. Now, what does it mean? It means that actually we need to average over different positions here on the line. But now, how do we do that here? Let us take 2 nearby points here. Let us take this point and the neighboring point here. So this draw an arc here, like that. This draws an arc. And now, actually, the surface area of the arc is proportional to the number of points on the surface. Do you agree? The longer arc we take, the longer the larger surface area will have a sector. Always proportional to the angle. Both are proportional to the angle. So the number of points is proportional to the number of points on the arc. And now this is also into another sector here, like that. And because it's compressible, the same surface area here. So this has the same A using compressibility. And now you can see that instead of averaging over the points here on the arc, we can average over surface area. Averaging over the number over the points on the arc, we go to averaging over and now again I need to restart. That's already annoying. I don't know, when the first half of the election it was fine. Second half, Okay, by next time I update the software, we'll see if it still persists.
Are you sure it has to do with the software? Maybe it's something with the pen? No?
Pen is there, it's some interaction between, I think some interaction between the pen and the software. So maybe updating works, maybe not, we'll see. And then again, I think it's quite a good software, a piece of software, and I haven't found anything which just default whiteboard Microsoft thing. I think that's not as good as flexible. Now at least I got out how do I. Actually, I more or less figured out when it goes wrong. It goes wrong when I write too fast. When I wrote something, and when I type something what I already wrote, then it freezes, or something like that. I think it might be also caused by the lag between computer and the screen. Probably. Averaging over here, over A. Right? And now, don't tell me it's again thing.
Are there any buttons on the pen? Maybe?
Huh?
Are there any buttons to press?
No, just when I move now here, it starts like something remains in press state, and then if I, maybe. Slow down, maybe. Then again, our time is also coming back in. Maybe the length of the file has also something to do with it. Because it just would explain why it initially works fine, but towards the end of the lecture it becomes, I think that's good. Okay. Otherwise, we surface here, yeah. Okay. Now let me take new screen, maybe it's much better now. So once again, we have circle like that here. We have long ellipsoid like that here. And then here is our initial segment. And here is our final segment. And now we want to average the length here L. And now averaging will be performed by integration over angle. So here is alpha. This is alpha. And here is also alpha. Okay, so this here is d alpha. Angle over there is d alpha. Now surface area dA. dA equals L square multiplied by d alpha and 1/2, isn't it? Do you agree that this is a surface area differential here? Raise your hand if you think so. Okay, so so we can proceed with our calculation. Now average of L to the power of -2 is averaging over angle, which is 1 divided by 2 pi. Integral from 0 to 2 pi. L to the power of -2. Divided by not 2 pi. Total area. This is total area is pi AB. The surface area of the ellipse, right? Because they create dA divided by A. Probability is B right here. dP is dA divided by pi AB. Right? Probability makes a percentage of points on the arc is related to the surface area. L to minus 2 and then multiplied by that 1/2 L square d alpha. And here you are, L cancels out. And now this integral d alpha is now what? This is pi. Integral is pi divided by pi AB. Well, pi AB is the total area. Total area is actually the initial area as well because its overall is incompressible. This we have AB is here. So you can see that L to the power -2 is conserved. Average of minus second power of the L links. Okay, so why did you consider this? It is because this one has a nice and very simple exact result, which comes out on the one hand, even if you have a complicated large deviation function, a simple thing which comes out on the one hand. On the other hand, because all the mixing depends on stretching. So this is also part of the stretching. So here, if we take L minus 2, actually, what I emphasize on are very small lengthening, because you see L minus 2 is dominated by very small values of L, when L to minus 2 becomes large, right? Okay, so the lesson to take thus far from here is that, let us make a small conclusion. Log normal L and length of material length. Normal. Second is that for extreme events, and K not small, Kuba number not small, you need to consider large deviation function. You need the large deviation function. And so 3, we still have L to minus D. D was here 2, but if you take a 3-dimensional space, D becomes 3. L to minus D is constant if you average. You have a statistical conservation law. If you average over all the directions, then you have constant. Now, we're supposed to also talk about bachelor's law, but our 2 hours are more or less over now. Shall we finish? Next time then about bachelor's law and things which come after. Things which come after, we can keep a little bit faster because we already discussed quite a lot about small and large Kuba numbers. One of the topic is so-called Streitner flows. Streitner flows are ideal mathematical model of flows, which are a very small, infinitely small Kuba number, basically, like delta correlated in time. And this is also very a quite important thing because again, okay, about that next time. About that next time. Bachelor's law and the Streitner flows are next time.
Thank you very much.
Yeah, so and once again, next time, nota bene, next time is after 2 weeks because I am away. I am arriving next Wednesday, but later than the lecture time. So we will not be having able to lecture. So after 2 weeks.
Meanwhile, I still strongly recommend having even not having a big caps work on your homework. I promise this is nice. You will be getting nice pictures from that. And if you go also to the bachelor's law, then there is another homework based on your simulation code. You need to check if you have bachelor's law coming out from that. So this is another like two coding tasks which are, well, depending on your skills, are easy or not that easy, but you can take your time until the end of the semester to finalize those. Okay, see you next time.
Paris.
Tomo, do you want to ask something? Fine.
No, if you could just send the lecture slides as well, that would be appreciated. Thank you.
Well, fine. So, do you like thus far what you have what we have had here?
Yes, yes, very interesting. Thank you.
Okay, that's good. Then yeah, have a nice time and after 2 weeks.
Thank you.
Bye.